In geometry, an angle is a union of two rays sharing a common endpoint. The Greek letter theta is a variable that commonly stands for the measure of an angle. The angle theta, pictured above, is a measure of the amount of rotation between the two rays. Angles are not measured in units of distance such as meters, feet, and inches. Instead, they're a dimensionless quantity which conveys to us the extent of a rotation or revolution. Perhaps the most simple and intuitive unit for measuring angles is the unit of revolutions. Find the number of revolutions pictured in each situation below. I'll do the first one. So we could think of this as a top-down view of perhaps a moon orbiting a planet or a planet orbiting a sun. And we just want to trace the path and see how many times it goes around. I count 1 time, 2 times. So that's going to be 2 revolutions. But we want to give symbols for this quantity, and we'll call it delta theta. Delta theta stands for what's called an angular displacement, and that could be measured in revolutions. Delta theta is 2 rev. Try the others for yourself, and then I'll give my answers. Alright, so in the next case, the object travels once around, so that's going to be a delta theta of 1 rev. This one makes 3 rev, 3 revolutions. Here we could use a fraction or a decimal, 1.5 rev. And the last one was 2.75 rev. Okay, that's the unit of revolutions. But angles can also be expressed using the degree system, with the convention that 1 revolution corresponds to 360 degrees. Now that's a totally arbitrary number. It could have been any number. But with 360 degrees, we see that traveling a quarter of the way around the circle corresponds to 90. Halfway around the circle corresponds to 180. 3/4 of the way around would be 270. And then if we make a full revolution, we've gone 360 degrees. Let's find a conversion for converting revolutions to degrees. So one way to write this would be, we want to find an angle in degrees. And we start with an angle in revolutions. So the question is, how do we convert from one to the other? We could do it with a conversion factor. Conversion factor has to be something divided by itself so that they're equivalent, and that would be multiplying by 1. We'll actually use this known equivalency above, that 1 revolution is 360 degrees. We'll put those quantities into our fraction. We just have to put the right one on top. So our theta here is going to be in rev, so we actually need rev down below. And we want to produce degrees, so we need degrees on top. So that makes it clear that the 360 goes up here and the 1 goes down there. So basically we have to multiply an angle in revolutions times 360 in order to find that same angle in degrees. Find a general formula that would allow you to convert degree angles to angles in revolutions. I'll let you try that and then I'll give my answer. Alright, so this is going to be similar to the one above. We want the theta in revolutions, and we start with a theta in degrees, multiply by a conversion factor, but this time the revolutions goes on top and the degrees go on bottom. So if we know an angle in degrees, we just divide by 360, and that'll give us the angle in revolutions. So since we already know that this is 2 rev, 1 rev, we already know these angular displacements in revolutions. Can you find the angular displacements in degrees? I'll do the first one. We want to start with our 2 rev and then multiply by the conversion factor, 360 degrees per revolution. This will be an angular displacement of 720 degrees for the first one. I'll let you try the rest, and then I'll give my answers. Alright, so following that same approach that I used, here we would have 360 degrees. It's 1 time around the circle. Here we're going 3 times around the circle, so that's going to be 1080 degrees. Here we'll have 1.5 revolutions, so that'll be 540 degrees. This one turns out to be 990. There's one more type of angle that we should be aware of, and that is the unit of radians. So if we consider a unit circle where the radius is 1, it can be shown in geometry that for any circle whose radius is 1, the length of the outside perimeter of that circle would be 2 pi, which is approximately 6.28 radians. And it's 6.28 times the size of the radius. That's always true for any circle. Use the conversion of 1 revolution equals 2 pi radians to find a general formula that would allow you to convert angles in revolutions to angles in radians. I'll let you try it and then I'll give my answer. Alright, this time we wish to produce an angle in radians. We're going to start from an angle in revolutions, multiply by a conversion factor. The conversion factor is made out of the quantities in our known equivalency here. We want to cancel revolutions, so we need rev on bottom. And we want to produce radians, so we'll put that on top. So 2 pi goes on top, 1 goes on bottom. Multiply the number of revolutions times 2 pi to get the radians. I'll do the first conversion here. We'll start with 2 rev, multiply by the fact that there are 2 pi radians in every revolution. So this is going to be 4 pi. Now, you don't actually have to put radians as a unit on these. Any angle is assumed to be radians unless otherwise specified. Go ahead and try the others, and I'll give my answers. Okay, so here we have 1 trip around the circle. That's going to be 2 pi radians. This one ends up being 6 pi. Here we have 3 pi. This one would actually be 5.5 pi. Okay, so that brings us to what is an angle in standard position? An angle is measured in standard position when it's measured counterclockwise from the positive x direction. So luckily, one of the rays of each of these angles does point in the positive x direction. So in order to do the standard position angle measurement, all we have to do is see how much rotation there has been from that point. So for this one, we'll go from the positive x direction to that terminal ray. And we'll do the same thing here, and we would do the same for all the others. Now here, our circle has been marked every 30 degrees and every 45 degrees. So, if you recall, quarter way around the circle was 90 degrees, halfway around was 180, 3/4 of the way was 270, and if you go all the way around, it's 360. So it's marked every 45 degrees, and so this right here would be 45 degrees. Here we'll have 30 degrees and then 60 degrees. So this is an angle of 45 degrees. The next one's going to be 120 degrees. See if you can find answers for the next two, and then I'll give my answers. Okay, so one of the tricky things about standard position angles is we want to measure them from the positive x-axis, but counterclockwise from the positive x-axis. So, while it may be tempting to give an answer of 120 for this, what we're looking for here is to measure it counterclockwise, and that would be 240 degrees. And so here, if we go all the way around, we'll find 300 degrees.